So here we've got a potato. We've taken the potato from a pot on the stove and we're cooling it off so that we can eat the potato. Very exciting. Everybody likes to eat potatoes. Maybe not everybody, but some people. We're given some information in here. One, that the initial temperature of the potato as soon as we take it out is 91 degrees Celsius. That is the definition of a hot potato. So we also know that the internal temperature of the potato is always greater than 27 degrees for all t values greater than 0. So all t values we're concerned about. Potato is always 27 degrees or 1. And we know that the internal temperature of the potato is modeled by the function h. And h satisfies this differential equation they've given us as dh dt is negative 1/4 of h minus 27. Okay. Good? Conceptually good? Okay. So if we wanted to know the temperature at any time, we'd have to know what h was. In order to find h, we'd have to solve the differential equation. We're not asked to do that. Yeah. In fact, we're not actually ever asked to do that with this particular differential equation. That's fine. We will deal with that. First thing we are asked is very similar to the other differential equation FRT, which is to write an equation of the tangent line, which should be pretty straightforward. What do we need to write the equation of a tangent line? We need a slope and we need a point. And we need two things, slope and a point. So first thing, we'll go with point. The point that we're going to use should be the point that is given to us in the problem. What point is given to us in the problem? The initial condition, when the time is 0, the temperature is 91. How do we find the slope? Just like with the other differential equations, we just use the differential equation, right? We have dh dt, and we want to know what that is, because that's the slope of h at the point when t is 0 and h is 91. And dh dt was negative 1, was it one positive or negative 1? Negative 1/4 of h. Well, what's h in our initial condition here? 91. So negative 1/4 of 91 minus 27. 91 minus 27 ought to be 64. So this is negative 1/4 of 64, which is negative 16. Everybody good with that? People at home good with that? People here good with that? People at home, are you good with that?
Yes.
Zoom good? Good Zoom. Okay. All right. So now we write the equation. Y minus 91 equals slope t minus 0. You don't need to write the t minus 0 if you don't want to. Just write the t, that's fine. And then it says to approximate the temperature when t is 3. 3. Yeah. T equals 3. Approximate the internal temperature when t equals 3. So we plug in 3. Y minus 91 equals negative 16 times 3. That's negative 48. Negative 48 plus 91. Plus negative 48 plus 91 should be 48. Right? Pretty straightforward, I hope. Yeah? Hopefully pretty straightforward. Okay. Wonderful. Anybody at home have an issue with that?
We wouldn't use h for y, would we?
No, you would not need to write an h for y, because it says write it. Well, let's see what it says. You could probably. Yeah, equation for the line tangent to h at t equals 0. So you want to use y.
Okay.
Question? Let's see here. The first part of that, I have to look it up specifically for this one. Let me look at this. Probably. Oh, that's not the right one. Where's it go? There it is. Yeah, these are big here. All right, let me look up the scoring guidelines. Give me 1 second. It's really easy to find this one. this was 2017. All I searched for online was potato AB. Here it is. Where? 3 points. Oh, okay. I would have called this 2 and the next one 2, but they gave it 3 and 1. So they gave 3 points for this. They said that getting the slope was 1 point, getting the tangent line was 1 point, getting the final answer. Good? Everybody good there? Yeah. Part B asks us something a little different than the other one said. Use the second derivative to determine whether your answer from A is under or overestimate. So first off, we have to find the second derivative. And I found over the years that people, for some reason, have a difficult time finding the second derivative in these real life differential equation problems. Okay? So we have dH dt is negative 1/4 times h minus 27. We want the second derivative, which means we need to take the derivative of this with respect to the t.
T.
That's right. Okay. First off, the negative 1/4 in the front there is just a constant. It's like a coefficient on this thing, right? So I can just leave that there. What is the derivative of h minus 27 with respect to t? dH dt. We're taking the derivative of h with respect to t, which means we take the derivative of h with respect to h, that's 1, and then multiply that by dH dt. And then the derivative of the 27, no matter what variable you take the derivative of that with, it's 0. This is not the answer that they would want. They would want you to write it as negative 1/4 times negative 1/4 times h minus 27. Plug in the dH dt that you originally had, and you get 1/16 of h minus 27. Okay. Now, that's all great, but the question asks, is this an under or an overestimate, your answer from part A? And so we're going to take a minute here and think about that and look at a couple of different cases. Number one, if they ask you about the second derivative, and then whether that's an under or an overestimate. Well, whenever you talk about the second derivative, what are you usually talking about with regards to the function?
Concavity.
Concavity. Good. Yeah, so we all agree that the second derivative is that concavity. Okay. So, actually, we'll do this here. What can you tell me about the internal temperature of the potato for all values of t greater than 0? It's always what? Always greater than 27. We know that h is always greater than 27, according to what they told us in the problem. If h is greater than 27, what can you tell me about 1/16 of h minus 27? It's always positive. Everybody agree with that? Okay. Well, if the function's second derivative is always positive, that tells you that it is always concave up. So we talked about this many, many years ago, or months ago or something. Here's a function that is concave up. What have we done with the function that's concave up? We have drawn a tangent line to approximate it. That's what we did in part A, was we did a tangent line somewhere on this function. And that's right there. Tangent line there. And we've used that tangent line to approximate the value somewhere else. Right? We use that tangent line to approximate the value over here. Didn't we? That's what we did. We used the value at t equals 0, which is not what I drew, but that's fine. to approximate it somewhere to the right of there. Whether it's to the right or to the left, it doesn't matter. When the function is concave up, your tangent line's value at A will always be less than the true value of the function. Okay. This is our function. This is our tangent line approximation. The tangent line approximation will always be less than the true value of the function. This is something they love to ask about in the differential equation FRQs. They'll ask about the second derivative, and then you'll have to use that concavity to show something. It will occasionally also show up in other FRQ questions, something about tangent line approximation. What if the function is concave down? Not very well drawn. There's my tangent line. Okay. If I use the tangent line to approximate the value of the function at a place where I'm concave down, then it should be above the true value, shouldn't it? So this is concave up. Tangent line is an underestimate. Concave down. Tangent line is an overestimate. I would almost guarantee that they will ask you this in some capacity somewhere in the free response questions, most likely in the differential equation. Okay. Sometimes they also like to talk about a secant line. What's a secant line? There are 2 points, right? There's my secant line. So sometimes they will like to ask about a secant line and have you approximate something using the secant line. If the function is concave up, and I use the secant line on that interval to approximate the value of the function, secant line is going to be greater than the true value. So we would say it's an overestimate if it's concave up. But if it's concave down, that secant line is going to be an underestimate. Everybody in here good with that? So this shows up, and this is on that sheet, that document that I gave you also. People at home, are you good with that?
Yes.
Great. All right. So we go back where we were a long time ago. Our function was concave up. And if you don't remember offhand, it's really easy. Get the picture. Get the tangent. Get the tangent line. Get anything concave up, get the tangent line. You can see the true value is greater than the tangent line. The tangent line is an underestimate. And that's exactly what you would write. You would say that the tangent line approximation from part A is an underestimate of the true value because the second derivative indicates that the function is concave up for all t greater than. That makes sense? And they gave 1 point for this. And we spent a lot of time talking about it, but that's 1 point that you want to get. That's 1 point that's the difference between your 4 and your 5, or your 2 and your 3. Now 4 and 5, hopefully. Any questions there? Why did I take it out? It's just a coefficient in front of everything, so like it's, I could have. I'm taking -1/4 and then times h minus 27. I want to distribute the -1/4 through to both of them. You could, and then you have -1/4 h minus 27/4, which you do, plus 27/4, that you take the derivative of. And so your derivative of -1/4 h would be -1/4 h. Treating this like a function, but -1/4 times the derivative of this function. So either way you want to do it. Yeah. Oh, well, okay, yeah, so the potato is cooling off, but it's The graph that I sketched wasn't specifically of the potato. That's just, I just sketched something that was concave up because we know we were guaranteed that it's concave up. And it doesn't matter, you know, it doesn't matter what it looks like. It would have looked more like this. It would have just been this side of it, but it's cooling off. Right. But still, either way, wherever my tangent line is, the value of my tangent line at any place near there is always less than, still under it. Whether I'm on the left or the right, you know, whether it's decreasing or increasing, that doesn't affect the under or overestimate, the concave. Does that make sense? Yeah. No. I was just sketching any concave up curve. Everybody good with that? Yeah. All right, great. So,
Mr. Bachelor,
yeah.
do they penalize wrong answers in the free response questions also?
They do not penalize. I mean, you just don't get the points. Oh, I don't know what that was. But no, they do not penalize you for it. And in fact, let's say part A of some free response question is really difficult and you fail it and you screw it up and you get it wrong. But part B requires you to use your answer from part A. Well, you could still get the points for part B, even if you take your really crappy, awful, incorrect answer from part A and use it in part B, but do everything for part B correct, other than you put the wrong number in because you got the wrong value for A. They'll still give you the points for part B. So in fact, they try really hard to give you the points. And no penalizing for missed things in any of the tests. All right.
So, Mr. Bachelor,
Oh, yeah.
if you really don't know what to do for part A, just randomize, like put some random math there and then try to do part B based on that.
Yep, go for it.
Okay.
No clue what to do for part A, right? I don't know, right? 7x plus 3 at x equals 1 equals 10. And then use 10 for part B because you needed an answer from part A. And they will just laugh at you for part A and not give you any points. But then if you do part B right, you'll get points. Just put something there. If you don't put something there, though, then you're screwed. You can't do part B. So put some garbage crap there that's totally wrong if you don't know how to do it. I mean, better than that, make sure you know how to do it. But like, if you don't, just put some crap there and use it for later parts. Okay. Answer your question. Okay. Part C was asking us to solve, not that differential equation though. It gave us a different model for it, I believe. It said, we got a new model, negative g minus 27 to the 2/3 power. And we wanted to solve that differential equation and then use that to approximate the value of t. So that's our goal here. We've got the new differential equation dg dt equals negative g minus 27 to the 2/3 power. Okay. And I think it's important for us to just briefly talk about this, that because the variable on the right-hand side, the only one that we happen to have, which is g, is the top part of our differential here, that tells us that this is a separable differential equation. And we must bring the g over to the left-hand side with the dg, and we must take the dt and bring it over to the right-hand side. Okay. So if you have dy dx equals something with y's in it, you know that's a separable differential equation. If I had dg dt and this was just t over here with some other crap, I could just integrate, and that's fine. But because this g that's in the numerator there is over here, I have to separate the variables. Everybody good with that? Okay. So we end up with dg over g minus 27 to the 2/3 equals negative 1, we'll say negative 1 dt, negative dt, or just negative 1 dt, same thing. And now we will try to integrate both sides. Yeah, the right right-hand side should be very easy. What's the integral of -1 dt? Should just be -t plus our constant. And what about on the left-hand side? That one, we're going to rewrite when we try to integrate this. I'm going to rewrite that as g minus 27 to the -2/3 dg. Why do I want to do that? Because then I can use the, well, we're gonna do a u sum, which is the chain rule in reverse, but yeah, we can just use the power rule once we do the u sum, right? The u sum is going to be u equals g minus 27. du is dg. So really, I just got an integral of u to the -2/3 du. Right, and so what's the integral of u to the -2/3? We go up by a power of 1, so -2/3 plus 1 is 1/3. So that's u to the 1/3. And then we have to divide by 1/3, which is the same as multiplying by 3. And so there's our integral. Now we need to do what? What's the next step here? Find the c, right? Find the c given our initial condition that when t equals 0, the potato's temperature is 91. So 3 times 91 minus 27. Already did that at 64 seconds. T was 0, so that's the 0 plus our constant. And what does that give us for our constant? That's the cube root of 64, which is 4, times 3, which is. Everybody good with that? Any questions or issues there? Okay. So we've now got 3 times g minus 27 to the 1/3 equals -t plus 12. Everybody good there? And now we just solve for g. The first step in solving for g will be to divide by 3. Next step will be to cube both sides. And the last step will be to add the 27. There it is. There's your solution. And then the last thing it said, tell us what the temperature of the potato is at t equals 3. So we'll say 3 is 27 plus 12 minus 3 over 3 cubed. Well, 12 minus 3 is 9. 9 divided by 3 is 3. 3 cubed is another 27. So 27 and 27. 54 degrees. Good or no? Anybody any issues there?
When we were separating the equation in the beginning, could it have worked if we also brought the negative over?
Yes, you could do that. That would be fine.
Okay.
Sure. My personal preference is to leave any constant on the right-hand side.
Mm-hmm.
Right? Unless there's like a good reason to bring them over. But it doesn't matter. Either way you do it, you should get the same. You should get the same final equation for g. You might end up with a different constant, depending on if you do that. But in the end, it'll all work out to be the same.
All right. Thank you.
Yes, I'll go. Philip, you get on the stage? Yeah, okay. Yes, that is what it said. It said find an expression. No, here it is. Yeah, so satisfies the differential equation, and g of 0 equals 90. So that's the initial condition. Everybody good? Everybody here good? Zoom, are you all good? Zoom good?
Good.
Good. Zoom. All right. That's the potato problem. It's not so bad, is it? It's not so bad. Why did those kids in 2017 whine and complain about the potato problem? I don't know either. Bunch of whiny, complaining kids. All right. Here is the baby bird problem. This is the baby bird. We're going to learn about its weight and how its weight increases. So I would like to give you guys 15 minutes to work on this one right now, because that's how long you have on average for each differential equation, or for each free response question, I mean. And then we will go through it. You'll find that it is similar in some ways, but also a bit different. All right, ready to go. If you can't, can you guys see it in here okay? I don't know. Maybe. Okay. First off, is the bird gaining weight faster when it weighs 40 or 70 grams? Well, what is the rate of change of the bird's weight? It is their derivative, right? That's dv dt. So we just need to figure out is dv dt and d equals 40 or dv dt at d equals 70 larger. So a little different than the first one. Actually, probably easier than the first one. Right? So plug in 40, what do you get? Well, plug in 70, you get 6. So you'd say faster when it weighs 43. And you'd give an explanation. You'd say because the rate of change at 40 is 12 and the rate of change at 70 is 6. And 12 is more than 6. Okay. Easy enough, yeah. You should try to write your explanations in complete sentences. Yeah, I mean, it doesn't have to be like, yeah, if it's not complete sentences, it's not the end of the world. But like, just be, you know, write like you're trying to make somebody that has no clue what they're looking at understand what they're looking at. Everybody good with that? People at home good with that?
Yes.
Yes.
Oh, 2 people. All right. Good question. I'll look it up in a minute. Let's do part B and then I'll look it up after. Finding the second derivative. This should be very similar to the last one where we found the second derivative. So that should be our second derivative of b with respect to t. Should be, well, the derivative of 1/5 of 100 minus b. We could distribute the 1/5 through again if we like we talked about last time if we wanted to, or we could just leave the 1/5 out in front. The derivative of the 100 is 0, and the derivative of the negative b is negative db dt, which gives us a second derivative of negative 1/25. Right, that's the 1/5 times the negative 1/5, then 100 minus b. Everybody good with that being the second derivative? Okay. Now, why can't this graph work? Must have to do with concavity, right? Because this is the second derivative that they asked us to find. So what can you tell me? Well, the b values are always between 20 and 100. So for b between 20 and 100, the second derivative is always going to be negative 1/25 times a positive number, which will always be negative. If it's always negative, it should always be concave down. Is that part of the graph concave down? No, that part of the graph is concave up. So there's your explanation. The second derivative indicates that it should always be concave down, yet half of that graph is concave up. Good or no? Everyone's good with that? Wonderful. All right, what about part C? Oh, I was gonna look up your thing. Let's look up your baby bird problem. This should be easy to find. We're just gonna search for baby bird, AB. This was from 2012 apparently. Part A is worth 2 points. 1 if you use dB/dt at all, and 1 for the right answer with the reason. And then part B here was worth 2 points, 1 for the second derivative there, and 1 for the reasoning why. Concavity. Part C will be worth 5 points. Everybody good with A and B? People in the Zoom, you good?
Yes.
Yep.
Good.
People here, you're good? All right. Next is then dB/dt equals 1/5 of 100 minus b. And since we have a b, and the b is the top part of our derivative, we need to separate the variables. So this should become dB over 100 minus b equals 1/5 dt. If you choose to bring the 5 over, you can. I choose to leave the constants always on the right-hand side personally. That's up to you. So we integrate. Right-hand side is easy, 1/5 t plus your constant. Left-hand side requires a use of. Okay. We're going to say u equals 100 minus b, which is going to mean that du is negative dB, which means we need to put in a negative and a negative. Yes? Which is going to give us negative integral. Negative dB is du, and 100 minus b is u. So we have the integral of du over u with the negative in front, which should be negative natural log absolute value u. Or 100 minus u. Everybody good there? Okay. And let's see. Up to this point, that's worth 1 for separating the variables, 1 for the 2 correct antiderivatives, 1 for writing plus c. So 3 points so far. Fourth point is for finding c. So we know that when t is 0, what was the weight 20? Is that right? Yeah. So we end up with negative natural log 80 equals our constant. There's your fourth point right there. Then we finish solving. Negative natural log absolute value of 100 minus b equals 1/5 t minus the natural log of 80. And from there, first thing is we'll divide by a negative. So that's going to give us natural log absolute value of 100 minus b equals, it should be a positive natural log of 80 minus a 1/5 t now, is that right? How do we get rid of the natural log on the left? Exponentiate. This just becomes absolute value of 100 minus b. That e to the ln 80 minus 1/5 t is the same as e to the ln 80 times e to the negative 1/5 t. If you use exponent rules, and then e to the ln 80 is just 80. So we've got 80 e to the negative 1/5 t. We need to clear off the absolute value. If I clear off the absolute value, I could get a positive or a negative over here, right? When you clear off the absolute value. So we have to make sure that we get the right one. Well, 100 minus b is what? With our initial condition, 100 minus 20 with 80, right? We need 80 equals 80 e to the 0. That makes sense, right? We don't want to put a negative in front of that. That'd give us 80 equals negative 80. So we're just going to call this 100 minus b. 80 e to the negative 1/5 t because of our initial condition. I'm going to add b. I'm going to subtract the 80 e jump. So we end up with 100 minus 80 e to the negative 1/5 t. And that's that. Good? Questions? Zoom questions? People here? Questions? Fifth point.
Wait, so it's positive because you can't have negative time, right? Like that's the reason why it's not negative.
Not because you can't have a negative time, but because at this point, When I come down here, where we could have a positive or a negative, like theoretically, but we need to pick the one that when we plug in our initial condition, which was 0, 20, makes that still true. So if I plug in 0 and 20, I get 100 minus 20 equals 80 e to the 0. And so I don't want to put a negative in front of that 80 because that gives me 80 equals negative 80.
Okay. All right, thank you.
Any other questions, anybody? Okay. Tonight, I would like you to, I believe it was originally page 9 of this, but it's this problem about trash. Okay. I believe it's page 9 of this stuff. Okay, so do this one for tonight. We are going to start talking about rate FRQs. In fact, I'd like you to take a look at the first 2 rate free response questions from the document that says rate FRQs in Google Classroom. Do pages 1 and 2. It's about a fish and an escalator. So you have 3 problems to do tonight. One is this problem about trash, and the other are the first 2 pages of the rate FRQs. So you got trash, fish, escalator. TFE, trash, fish, escalator. You'll all remember that? Trash, fish, escalator. Trash, fish, escalator. TFE, trash, fish, escalator. All right. If you have questions in Zoom, you are welcome to stay and ask. Otherwise, you're good to go.